All right, so the next talk is from Andy Marszewski on the mass metallicity relation in fire at high redshift.
Is this volume okay? Hey, hello, everybody. Thank you for having me. My name is Andy, and I'll be talking about the high redshift gas phase mass metallicity relation in Fire 2. This is work I've done as a PhD student at Northwestern University Sierra, along with Claude Andre and Jason Sun, as well as other members of the Fire collaboration, including Robert Feldman, who is so graciously chairing this session right now. So to begin with a little bit of background on the gas phase mass metallicity relation, this is, of course, the relation between stellar mass and gas phase metallicity of galaxies. And this relation has been very well observed in the local universe around redshift 0 by large-scale surveys such as SDSS, shown here on this plot with the black line, where we see this power law relation between gas phase metallicity and stellar mass, which then levels out to a much more shallow relation at high stellar mass. We've also, via a number of samples, characterized this relation at cosmic noon. So 3 of those samples are shown here by the pink, the orange, and the red lines. And again, we observe this power law relation between gas phase metallicity and stellar mass. And then finally, now thanks to JWST, for the first time, we are making observations at very high redshifts, which characterize the gas phase mass metallicity relation. So here from this Curdy et al. 2023 paper, they provide 2 different samples here shown in yellow and blue, with yellow being from redshift 3 to 6 and blue being from redshift 6 to 10. And again, we see this power law relation, but with relatively weak evolution in the normalization relative to what was seen at lower redshifts. Okay. So these new motivations in this high redshift regime, these new observations in this high redshift regime have really motivated us to use simulations in order to characterize the evolution in the form of the mass metallicity relation at high redshift. And to do this, we turn to a suite of 34 high redshift cosmological zoom-in simulations from the Fire 2 suite. And these were originally presented by these Ma et al. 2018 and 2019 papers. But I'd just like to point out that this is the same suite of simulations that Jason Sun talked about earlier this week, where he used them to analyze the effects of Persei star formation on the high redshift UV luminosity function, as well as other observables of galaxies. These simulations have host mass halos between 10 to the 9 and 10 to the 12 solar masses at final redshifts of 5, 7, or 9. Most of them are run down to redshift 5. Baryonic particle resolutions in the simulations range from 100 to 7,000 solar masses, with the lower resolution corresponding to the more massive halos. But important for my work, these simulations include multiple channels for ISM enrichment, including quark collapse and type 1a supernova, as well as winds from OB and AGB stars. And also they include a subgrid turbulent diffusion model allowing nearby gas particles to exchange metals with one another. So we have these simulations, but which galaxies from these simulations are we actually analyzing? So in order to sample our redshift range, we analyzed each simulation from redshift 5 to 12 at integer redshift snapshots. We performed some cuts on the galaxies included in our analysis. Most stringently, we require them to have at least 10 to the 6 solar masses of stellar mass. And then we also exclude satellite galaxies and subhalos from our analysis due to the tendency of their environments to be very, very dependent on the environment of their host galaxy. And this yields us final sample sizes between 100 and 300 galaxies from our suites, depending on which redshift we're analyzing. Okay, so now into some results. So this is the gas phase mass metallicity relation we find in Fire 2 from redshift 5 in the top left, and then 8 different redshifts going all the way up to redshift 12 in the bottom right. Individual galaxies are shown by the individual orange points, but then binned medians are shown by the black boxes, with error bars representing the 16th and 84th percentiles. We also fit 3 different models. using the form, so 3 different redshift evolution models using the form shown at the bottom for the gas phase mass relation, which is just a standard power law where A is the slope of the power law and B is the normalization. And in the first model, shown in black, we allow both the slope and normalization to vary smoothly as a function of redshift. The red model, we only allow the normalization to vary smoothly as a function of redshift, and we keep the slope fixed. And then in the blue model, we allow for no evolution, keeping both the slope and normalization fixed. And for where you're sitting, it might not even be possible to make out the difference between these 3 models on our plots. And that's because we have found that evolution is very unimportant to include in our model. And so we have some evidence for weak evolution in the high redshift MZR. Okay, so that's one key prediction. But a second key prediction we've also found from this analysis is that we find increased scatter at the low mass end of the MZR. So if you look at our low stellar mass spins across all redshifts, they tend to have much higher scatter in them than the high redshift spins. And this is something we attribute to the high level of burstiness in fire galaxies at these high redshifts, and in particular, the susceptibility of these very low mass galaxies to having nearly all of their gas blown out by these intense episodes of feedback following starbursts. Okay, next I'd like to present some observational comparison with preliminary JWST results. So again, our best fit model is shown in black, and our medians are shown by the black boxes at 2 redshifts, redshift 5 and redshift 8, but every other point on this plot is observational. So the individual circles are individual galaxies that have been observed, but more important for comparison is are the binned means presented in these Kurti et al. And Nakajima et al. Papers shown in green and in orange. And what you can see is that pretty much all of the binned means at both of these in both of these redshift panels fall very close to our best fit line. And so we can sort of preliminarily say that we are finding really good agreement between observations and the fire model, at least from a normalization of the MZR perspective. But to sort of demonstrate the really rapidly evolving nature of this field and why it's so exciting, let's just take a look at the redshift 8 panel now. Just last week, this Chemerinska et al. Paper came out on the archive, where for the first time they sampled at this very high redshift regime the low stellar mass end of the MZR, and this is what their sample looks like. So these are just individual galaxies, but also the paper provided a really nice fit across all stellar masses, where they included the previously observed galaxies up here. And this is what that fit looks like relative to the Fire 2 model. And as you can see now, we can say preliminarily that in addition to getting the normalization in agreement with observations, we're also seeing that the slope is in very good, We're also seeing that the slope is in very good agreement. And so yeah, as we like to say in the simulation business, presumably our simulations have something to do with the real universe. Now back to safe space, because I'm going to compare with some other theoretical models from here on out. So this work again is shown in black, and now looking again, at the MZR in 4 different redshift bins, redshift 5, 8, 10, and 12, and also plotting models from Fire 1, Illustrious TNG, First Flight, Astraeus, and Flares. And if you sort of scan back and forth between these plots, what you'll see is that with the exception of Illustrious TNG, which does see some redshift evolution, the rest of these models have a developing consensus, which has also been seen in early observations, as was shown here, of a weakly evolving MZR at high redshifts. Okay, and a number of analytic models have been put forth to sort of explain the form and evolution of the MZR across cosmic time. I'll briefly talk about 2 of them here. The first is the leaky box model, which you essentially just consider galaxies to be leaky boxes of gas and of stars, where the stars enrich the gas with metals, but they're leaky because some of the gas and some of the metals can escape the box. And then there's the gas regulator model, which more explicitly takes into account the effects of inflows and outflows. But without rederiving anything, the real point here is that after making assumptions, both models allow you to write out an analytic form of the gas phase metallicity, and you'll notice that both of these forms are dependent on this parameter F gas, which is here defined as M gas over M star. And because of this, through these models, evolution in the MZR has been explained previously by using evolution in this F-gas parameter. And in particular, at low redshift, increasing values of F-gas with increasing redshift has been used to explain the decreasing normalization in the MZR, while at high redshift, very large or weakly evolving values of F-gas have been used to explain the weakly evolving nature of the MZR at high redshift. And because like all these things work in the right direction, it's sort of attempting natural conclusions that this is what's going on. However, what we've seen is that fire data contradicts this analytical picture, or at least finds it to be incomplete. So to begin with, a recent paper that came out from Luigi Vicini, who was a postdoc working in Robert Feldman's group, found that evolving values of F-gas are not responsible for evolution in the MZR from redshift 0 to 3 in Fire Box, which is a full cosmological box simulation run with the Fire 2 physics. Rather, evolution in the inflowing metallicity and outflowing metallicity are what's responsible primarily for the evolution of the MZR. And to add on to that, in our simulations at high redshift, what we found is that median values of F-gas do evolve with redshift, and they do so in a mass-dependent way, which is what's being shown on the panel on the right here. So we have log of F-gas plotted versus log of stellar mass. And what you see is this redshift evolution, which is mass-dependent in our simulations. And if the MZR were to be extremely susceptible to changes in F-gas, this should manifest itself as some redshift evolution in the slope of the MZR, which we do not see. So we can sort of say that it also looks like at high redshift that F-gas is not responsible for the evolution, or for the weak evolution of the MZR. So that's all for that work. I'd like to quickly mention some current and future directions that, of things I'm working on now. The first is investigating secondary dependence of metallicity on F-gas or on star formation rates at high redshift. So this is basically looking at any version of the fundamental metallicity relation being present in our simulations. We're also actively conducting analysis to find out what does drive the weak evolution in the MZR at high redshift. So it's one thing to shoot other explanations down, but we would like to provide our own explanation. And then finally, connecting element-resolved abundance relations to the physical processes that drive galaxy evolution at high redshift. Because we have these different channels of ISM enrichment, we can use individual element abundances to sort of explain the importance of different processes in driving the evolution of galaxies. Okay, and I'll just leave up my conclusions here, and I can take any questions. Thank you so much.
Okay, so we have time for questions.
Super nice work. I think one of the exciting things about Webb is, especially with gravitational lensing, we're actually pushing the MZR to 2 to 3 orders of magnitude fainter in stellar mass than what you have there. And I was wondering, it's pretty linear, right? But if you looked at lower stellar mass objects in fire, does it continue linearly all the way down, or is there a plateau or maybe even a break?
Yeah, so really interesting question. Oh, sorry, it's unplugged now. So what we have seen is that it remains. So we did look at low stellar masses, and like you mentioned, that Chemerinsky paper went all the way down beyond our lowest stellar mass, or our minimum stellar mass range, which was like 10 to the 6. They went down to like 10 to the 5.5, which is just incredible to see. And yeah, to answer your question, we have looked at lower stellar mass galaxies all the way down to 10 to the 4, I believe, and we see that the medians continue in a linear direction. However, there's even more increased scatter. So like we were seeing already, like the increased scatter. So it's almost as if you have, I think some people have been calling it like the mass metallicity cone in a way. So there's more galaxies that are like highly upscattered, but the median continues to drop linearly. Thank you.
Hey, thanks for the nice work. I'm not sure if I got it right, but when you compared the MZR relations for 2 different models, it looks to me that except T and G, most of them got it right. And so if you say that this is basically due to Z in and Z out, and they all have different feedback models, I was wondering what this is telling us. Or maybe I got it wrong, I don't know.
Yeah, so I wouldn't say like any one model is right. There's still a normalization and slope differences between the models. The one thing I was trying to point out is that all models predict this weak evolution at high redshift, except for Electris TNG, which does find some redshift evolution. So yeah, so I don't want to diagnose anything in other simulations, but I think one possible explanation is the resolved ISM in fire is what gives rise to this like extremely bursty star formation, which is sort of prevents gas from hanging out in galaxies too long, because you have these intense episodes of bursts, and the feedback that follows them blows out a lot of the gas, preventing gas from just hanging out in galaxies and collecting metals. I think simulations that don't resolve the ISM might have the problem of not having these intense feedback bursts, which drive out a lot of gas, and so allow gas to hang in galaxies and evolve, collect metals and evolve up the MZR. That's just a guess. Again, I'm not diagnosing what's up with Electris TNG.
All right, let's thank Andy again.